All right, good morning. We're 8:05. We're going to start, even though there's only 7 people here. We got a lot of stuff to go through today. So, hope everybody had a good weekend. Um, and we can start with questions, but let me tell you what I plan to go through today. I want to talk about homework 2 that you turned in last week and that I just posted grades over the weekend. So I want to go over that. I want to talk about any questions on labs. And then I want to move forward with new material that will take us up to the next homework and the next lab. So I'm just planning to keep moving forward through stuff. But if you have any questions up front, let's talk about those first. Because specific questions are always better than just kind of listening to me lecture. Questions on lab 3.
I have a question.
Mm-hmm.
Um, how do you translate essentially a sequence of A's and A naughts for an equation into a physical kind of circuit?
So you mean if you have an equation and you want to go to a circuit?
Yeah.
Sure. So let's suppose we have something like this. And this is a sum of products. Sum of products is a really easy expression to translate into an equation. Comment, question? Okay. So naively, if we didn't worry about appearances, right, we could start to sketch a circuit like this by saying, here's A0. We know we want A1 to go through an inverter. So here's A1 bar, and we want to AND those together. So we could put them through an AND gate. And now this output of the AND gate represents this first term. And then we want A1 ANDed with A2. So we could take A1 here, A2, put them through an AND gate. That's our second expression. And then we want A0, A1, A2 bar. So maybe we'll do, A0 and A1. And sometimes, this is a little old school, but sometimes when you cross wires and you don't mean to make a connection, you'll see a little loop like that. If you're making good solid dots whenever there's a connection, you don't need that little loop there. But that's an extra way to show, hey, there's not actually a connection between this wire and that wire. So there's A0, A1, and then we want A2 to go through an inverter. And then those should get ANDed. And this output is our third term, and then we want the OR of those. So we can take these and run them through an OR gate. And there's your output F. And so that gives you a sort of logic diagram corresponding to an equation. And then if you need to have switches and LEDs and stuff, well, assuming that we want a 1 to light up an LED, we could put an LED in there, put in a 1K resistor, run the other side to ground. And then our switches, each of these, let me just do A2. This would get pulled up to 5 volts through a 1K resistor. And then we'd have a ground connection that we can make with a switch. And so this would be a switch for A2. So this input is normally logic 1. When you close the switch, it's a logic 0. and you do the same for A1, A0. So that gives you a logic diagram with switches and LEDs. And then if you want an actual wire diagram, like the last schematics that we asked for in the lab, then you need to say, how am I going to implement this with physical parts? So, all of these can come from a 74 LSOH, and this could be pin 1, 2, 3, pin 4, 5, 6, and I think 13, 12, and 11. And the inverter could be a 74 LSO4, and this could be 1 and 2, and so on. And so you label each of the gates as to what physical device they come from, and you label the pin numbers for each of the inputs and outputs, and put that information in the component ID block, project ID block in the bottom, and then you're good to go.
Thank you, Professor.
The other approach, if you have a more complex circuit, is take your inputs, run them vertically. So here's A0, A0 bar, A1, A1 bar, A2, A2 bar. And now we need 3 AND gates. Draw your 3 AND gates and just connect the inputs to the appropriate drivers. So we want this AND gate to be A0, A1 bar. So I'll draw a wire to A0, and I'll draw a wire to A1 bar. Here we want A1, A2. Draw a wire to A1, draw a wire to A2. And here we want A0, A1, A2 bar. Draw 3 wires. And then take the outputs of those, run them through an OR gate. And this one I messed up. That can't be U1. Well, I didn't label it. That's fine. This can't be U1 because it's a 3-input AND gate, but you get the idea. So this way is very methodical, right? This one we kind of lucked out. We didn't have too many things crossing over each other, but this is a very methodical, mechanical way to draw a circuit from an equation. We're going to come back to this week and look at it in terms of programmable logic. And so we'll be revisiting this type of layout. If you have 2 of the same chip and you utilize different connections on one versus the other, would you label them separately? So by chip, I'm thinking of one of these. And so when I have something in my component ID block like U1, I'm referring to an integrated circuit. And if this is a 74 LSO8, it has 4 AND gates inside. Which means that, since I need 2 AND gates, they could both come from the same chip, right? The same integrated circuit. But I'm indicating which pin numbers I'm using on that chip. So this wire right here would go to this pin, pin 1. This wire right here would go to this pin, pin 13. Remember, these chips are labeled counterclockwise, starting with the pin to the left of the notch if you're looking from above. And you can find that in the data sheet. But if I had, 5 2-input AND gates, I would need a second chip because one of these chips only has 4 AND gates. So I'd have U1, 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 and then I'd have another AND gate, maybe that's U4. So my 5th AND gate would be labeled U4, and I could start using pins from that package. But the goal of this wiring diagram is to give you a blueprint for how to build your circuit. And you don't have to know anything about K-maps, truth tables, logic equations, Boolean algebra, nothing. This is just a straight blueprint. U1 is this chip. Take this chip, put it in your proto board, run a wire between pin 12 and pin 2 of whatever chip U2 is. U2 is a 7404. Put that in your proto board. Now run a wire between that chip's pin 2 and that chip's pin 12. And you've got that piece of your diagram wired. And you can kind of blindly follow it without having to think about, all the stuff that went into making this. Awesome. All right. Well, let's go over the homework. And I've told you I normally grade one question from the homework. I graded 2 questions because this was kind of a long homework set, and there were 2 sort of main concepts I was after. The first was, dealing with sum of products, product of sums from a truth table, max terms, min terms, all of that stuff. And the second one was K-maps. And so I looked at questions 3 and 11 in detail. And let's just pull those up here. Let me move this to another sheet. So question 3, we're given a function of 4 inputs, and you're asked to write it in canonical SOP and POS form. So let's just jot down what this equation is, and then I'll show you my camera. So f of 3210 equals A3, A2, or A1 bar, or A0, ended with A3 bar. And so again, these apostrophes that you see in written, typeset form are kind of unfortunate, but they mean to negate the thing right before it. But I really recommend not using those when you're writing things on paper. Stick to putting a bar on top of things to say complement, right? That's a Boolean algebra notation. The quotation mark is just kind of a nod to the reality of typesetting, and it will get you into confusion sometimes. The quotation mark will start negating the thing on the wrong side of it, especially after you've done, a few hours of these types of questions. So I'm going to stick to putting bars on top. And so, easiest way to do this, make yourself a truth table. So we've got 4 inputs, and there should be 16 combinations. And about half the class, the biggest problem they ran into was filling out the truth table. And if you don't get the truth table right, then you're never going to get your circuit right. So this is worth going over. The left-hand side of people's truth tables looked great. That's a battle that's been won. So how do we fill out F? So my suggestion, and a few people took this and it seemed to work well for them. My suggestion is don't try to just write down what F is by calculating this 16 times, right? Humans don't do well with ones and zeros. Humans don't do well with doing a lot of arithmetic operations, logical operations in our heads, especially if you're going to do 16 of them, especially if this is one of several homework questions and this is one of multiple classes you're taking. It's just asking for errors. So break it into pieces, right? First, let's write down what A3 ended with A2 is. And so all I have to do is look at these 2 columns and just take the logical AND of them. And I know that when I do an AND, I need both things to be 1 for the AND to be 1. So the only time A3 and A2 is going to be 1 is in these last 4 rows. So these will be 1s. Everything else will be 0s. The other advantage of this is, if something goes wrong, if you inadvertently do an OR instead of an AND, right? It's really easy when someone's grading this to look at this and say, oh, you know, you did an or instead of an and. That's why every answer in the final column was wrong. But it's not that you didn't understand anything. It's that you made a mental typo here, right? Not a big deal. All right, let's write a column for this. Well, I still don't want to do too much work, so I'm going to make a separate column for A1 bar. And all I got to do to find A1 bar is just complement this column right here, A1. Well, I've got a pattern, 0, 0, 1, 1, 0, 0, 1, 1. So A1 bar is going to be 1, 1, 0, 0, 1, 1, 0, 0. And now let's do A1 bar or A0. And this will be 1 if either this column is a 1 or that column is a 1. So let's copy all the 1s from A1. So those are 1s. We don't know that these are 0s yet, but we know that they'll be whatever A0 is. If A0 is a 1, then this column should also be a 1. Well, every other row has A0 being a 1. So this should be a 1, this should be a 1, that should be a 1, that should be a 1, that one, that one, that one, and that one. And everything that's left is a 0. And now we want to take that column we just figured out, A1 bar or A0, and we want to AND it with A3 bar. And I could do another column for A3 bar. I'm running out of space though. But, well, I'll sneak it in here. I'll do A3 bar. And it's just the complement of this first column, so it's 1s on top. And then 0s on bottom. Right, so that's the complement of this column. And now I want to take this and AND it with that. Well, I just have 2 columns. I don't have to pay attention to anything else. Just take the AND of these 2 columns and write that down here. So I know all of these are going to be 0s because the second thing I'm ANDing with is a 0. And up here, this column is all 1s, so anywhere there's a 1 over here, I'll get a 1 coming out. So this will just give me 1, 1, 0, 1, 1, 1, 0, 1. Now we're almost done. Now we're ready to write F. And F is just an OR, and it's an OR of this column. Right, that's that term, with this column, A3, A2. So I just want to take those 2 columns and OR them together. So I'll get a 1, 1, 1, 1, 1, 1. And then this will all be 0s. But then if I have a 1 over here, I will also get a 1 out. Well, this is a 0, 0, that's a 0. This is a 0, 0, that's a 0. These are all 0s, so these are going to be 0s. And then these are all 1s, and so 1 ORed with 0 is a 1. So there's your final answer. So 1, 1, 0, 1, 1, 1, 0, 1, 4 0s, and then 4 1s. So one more time, by showing all of these steps along the way, if you got something totally different for your final value, I can figure out maybe how you got those. And I can figure out, is it a conceptual problem or was it just a typo? All right, because we've written 160 1s and 0s on this piece of paper. Really easy to make a mistake, right? And if one of those is wrong, the whole answer can be off. So showing your work is helpful here. All right, well, this does not give us our answer to the question. The answer to the question was expand this function to its canonical or standard product of sums and sum of products forms. So let's do sum of products first. And so to do a sum of products, you want to find the ones in your truth table. So these are A3, A2, A1, A0. And for simplicity, I'm just going to write down the min terms, where our output should be a 1, and then we'll put it into its canonical or standard form. So there's a 1 in these spots here. So remember, this is min term 0, min term 1, min term 2, min term 3, all the way up to min term 15. So in compact form, this would be the sum of 1, 2, 0, 1, 3, 4, 5, 7, and then 12, 13, 14, 15. As a product of sums, we would write down the max terms where the output should be 0. So this looks like max term 2, max term 6, and then max terms 8 through 11. So these are compact form. But before we switch to the standard form, what do you notice about these two equations compared to one another? Is there any relationship between these numbers and those numbers?
Whatever's missing from the top is there in the bottom.
Whatever's missing from the top is down here, and whatever's missing from here is up there. These are complements to one another. And that should be what you observe, because the min terms we're writing are the terms where there's a 1. And the max terms we're writing are the terms where there's a 0. And if every output here is a 1 or a 0, everything from 0 to 15 will be either a max term or a min term. And so we can start to see some ways to move from min terms to max terms, from sum of products to product of sums, and that can speed up some of these types of questions down the road. For example, if someone gave you a compact sum of products and asked you to write the corresponding product of sums, you can do it immediately. Just write down the product of all the terms that you don't see in the SOP. But if you didn't know that trick, you would take this, you would write a truth table with 1s in all of these places, and then you'd say, okay, where are the 0s? And you'd find out, okay, it's 2, 6, 8, 9, 10, 11. Alright, so let's put this in standard or canonical form. So F and so you basically write out the min terms for the expressions for min term 0, 1, 3, 4, and so on and so forth. So I won't do the whole thing, but I'll start. So min term 0, the rule is if you have a 0 in the corresponding input, write that variable with a bar on top. And so min term 0 would be A3 bar, A2 bar, A1 bar, A0 bar. Min term 1 will be the same, except A0 will not have a bar on top because it's got a 1. So it'll be OR A3 bar, A2 bar, A1 bar, A0. Min term 3, you have a pair of 1s here, so A1, A0 will be true, A3, A2 will be complemented. So A3 bar, A2 bar, A1, A0. I guess we can do them all. So, but if you know how to write these numbers in binary, right, the shortcut is wherever you have a 1, write the variable without a bar. Wherever you have a 0, write it with a bar. So every term here is going to look like this. So this will be term 5. This will be term 7. And then 12 through 15. And so this is minterm 0, 1, 3. For minterm 4, the number 4 in binary is 0, 1, 0, 0. So these will have bars on top. This will not. For minterm 5, this is 1, 0, 1. So these will have bars on top. These will not. Minterm 7 will have a 0, 1, 1, 1. And then here's 12 and 13 and 14 and 15. And the minterms we use are always the same. If we have an input variable, an input of 4 variables, we're going to have 16 minterms, M0 through M15. M15 is always going to be this and this and this and this. M14 will always be this and this and this and this bar. M0 will be this bar, this bar, this bar, this bar, all landed together. So after you've done enough of these problems, and there's a ton of these in the homework set you just did, so that may be enough, you start to not have to do the whole truth table and think about, this should be complemented, this should be true, this should be complemented. You start to develop, a kind of hardwired intuition for writing these equations. So anyway, that's the canonical or standard form of the sum of products. And then the product of sums we're going to have 6 terms here. Each of the terms is going to be a sum term. So it's going to look like A3 plus A2 plus A1 plus A0. And these are going to get ANDed together. And we're going to have 6 of them. So I'm going to fill these out, and then I'll put in the bars where necessary. Alright, so what's the rule for max terms? Max terms, if you have a 0, you leave the variable in its true form. If you have a 1, you complement the input variable. Right? So it's a dual to sum of products. Zeros are true, 1s are complemented. With sum of products, 0s get complemented, 1s remain true. So we're doing the opposite here. So for minterm 2, 2 in binary looks like 0, 0, 1, 0. So we're going to complement the A1. 6 in binary looks like 0, 1, 1, 0. So we're going to complement A2 and A1. And so on. 8, this is going to be a 1, so it will get complemented. The other terms don't. 9 will complement these two. 10 will complement these 2 bits. And 11 looks like this, and so we'll complement all 3 of these. And so there's a product of sums. So why are we having you spend time doing this? It's not so that you can get very efficient at doing this kind of thing, right? You're not going to have to do this, on a day-to-day basis in real life, no matter what your job is, unless you're writing textbooks maybe, or teaching and grading homeworks. But, the goal is not simply to be able to write this and write that. The goal is to understand the connection between this form and that form. between these min terms and these max terms to understand how they relate to one another, to help solidify an intuition for why, given a truth table, we can write a Boolean equation whose values match this truth table. Right? That's what we're trying to develop. And so this is just, wallowing in mud, basically. If you wallow in mud long enough, eventually some of the mud starts to stick to you. That's what we're trying to do here. So this is why you've got, these huge homework sets with lots of problems. The goal is not simply to look at the solved problem and try to mimic it, or to have a friend say, oh, just change the order of those things to the ones that you don't find here. Right? You're trying to understand this, and along those lines, it's well worth the effort at some point to convince yourself that these are correct. Right? To maybe take a simpler version of this, maybe something with 3 input variables, and actually write a truth table from this expression and convince yourself that you end up with the truth table that you started with. And the reason that this gives you the truth table is, for most people, easier to understand than the reason why this also gives you the truth table. But they should both give you the same thing. And the more you can sort of connect these two representations of a column of ones and zeros, the easier a lot of this other stuff is going to be. All right, so that was question 3, and it's sort of representative of a lot of other questions. And then question 11 was a K-map question. And so here we've got a function of 4 variables. And it's written in compact sum of products form, so it's 0, 4, 5, 7, 8, 10, 12, 13, 14, 15. And then we had 2 don't cares at 9 and 11. So let me go ahead and just write down the indices for these min terms using this truth table we already made. The ones and zeros are different, but I just want a mapping between min terms and values of input variables. And here again we can see a pattern. If we want to look at, say, min term 9, the values for the inputs 1, 0, 0, 1, well, that's just the binary version of the number 9. M11, well, we know that 11 in binary is 1, 0, 1, 1. Hey, that's the values for the input variables corresponding to M11. M15, 1, 1, 1, 1 is 15. That's the value for the input variables. So we can make a K-map without necessarily going through a truth table in the beginning. So let's do a generic K-map of 4 variables. And again, let's stick to A, B, C, D. Only one person went away from this, which is great. So if my inputs are ordered A, B, C, D, and the order is extremely critical here. When you're using compact form, how do I know if F4, right, min term 4 is, the term where A2 is a 1, or where A3 is a 1, or A0 is a 1, or A1 is a 1. M4, I know exactly one of my input variables is a 1, but which one? I've got to know what order these input variables are in. That's what this F parentheses A3, A2, A1, A0 tells me. So since we're dealing with F, A, B, C, D, I know that for min term 4, B is going to be a 1, C, D, and A will be 0. So the order of these is really critical, and that's another reason why you want sort of a standard way of doing this. So for my K-map, if my input variables are A, B, C, D, I'm going to put A, B here and C, D here. And then I'm going to put down all possible combinations, but I'm going to use this funny ordering where instead of my usual way of counting in binary, I'm going to flip these two rows. And I'm going to do the same thing with columns 0, 0, 0, 1, 1, 1, 1, 0. And if you want, you can think of each of these as being values of C and D that can help with filling things in later. Alright, so this I'm just going to create once. And if you have a way to make copies of it, you can just keep this and it'll work forever. But we want to fill in the ones and zeros and the dashes corresponding to this equation. Alright, minterm 0. This is where all of my inputs are 0. That's this box right here. So let me just lightly pencil in an M0 here. Minterm 1 is the box where A0 is a 1. Or this fourth term is a 1. In this case, it's D. And so these are 0, 0, 0, 1. This will be minterm 1. Bye. Have a great day. See ya. Minterm 2 would be where A, B, C, D are 0, 0, 1, 0, while 0, 0, 1, 0. This is minterm 2. And then minterm 3 will be where A, B are 0, 0, C, D are 1, 1. That's right here. And so go through all of the 16 terms in your truth table and you'll find the following. Same pattern here, 0, 1, 2, 3, 4, 5, 6, 7. And then minterm 8, this is where your first variable is a 1, everything else is a 0. Well, that's way down here. So this is minterm 8, 9, 10, and 11. And then 12, 13, 14, 15. And I don't want you to just blindly write this down and use it without understanding it, but if you go through a truth table like this and actually figure out where is M9, so it's a 1, 0, 0, 1. So I want 1, 0 and 0, 1 right here, there's M9. And once you do that yourself once or twice, this becomes second nature. And if you have this, right, you can fill out from a truth table by just going boink, 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 boink. And you can also count. So now if I want to actually fill in the zeros and the ones and don't cares from here, so I want minterm 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then 12, 13, 14, 15. And then for the don't cares, 9 and 11, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, sorry, that's a dash, 10, 11. So there's your ones and zeros. We didn't really talk about it, but I can tell you about it. So why is the 1-bit change from row to row necessary? If you go back to the truth table form of an equation, what we're looking for is adjacent rows that both have an output of 1. And so if I had this truth table for this equation, I could look at these two rows and I could say, hey, since these are next to each other, only one input bit is changing. In this case, it's bit A0. And so I can ignore A0 and I could say, hey, part of my output expression will be A3 bar, A2, A1 bar. And that'll take care of both of these ones. And so by writing our inputs in a way that from one row to another or one column to another, only a single bit changes, as long as we have two bits next to each other that have the same value, we know that we can write some expression that involves only one input variable changing. So it's a way to take this notion of things that are adjacent in some ordering of the input variables to make those visually adjacent to each other, so that our reptilian brains can look at it and say, oh, you know, these are right next to each other. Alright, so now we want to cover this. And our goal is to cover all of the ones and optionally cover the dashes and never cover any zeros. And so most people spotted this set of 4 ones. And that's definitely a good block to cover. And we've got another block of 4 ones right here. And that's a good block to pick up because, you know, we've got to pick up these 2 ones here. We could do just, you know, a little 1 by 2, but bigger is better, right? So make a 2 by 2 that covers those. And that leaves us with these 2 ones over here that are stragglers. Well, we could pick those up with, you know, a little 2 by 1. Or we could wrap around and pick up these ones over here and get a 2 by 2. But we're allowed to cover don't cares. And if we think of these as blocks that we're going to cover, we can get a 2 by 4. And bigger rectangles give you simpler expressions. So we'll go ahead and pick up that big block also. And so this first rectangle, well, A changes all over the place, B changes all over the place, but C and D are both 0. So this is C bar, D bar. And this middle 2 by 2, A is a 0 or a 1, so it doesn't matter. B is a 1. C is a 0 or a 1, so that doesn't matter, but D is also a 1. So that's the expression B ended with D. And then this block down here, 2 by 4 rectangle is a total bliss. So A is a 1 at every square in here. But B changes, C changes, and D changes. So this is just A. And so your final equation would look like this. A or BD or C bar D bar. And that's pretty much how all these K-map problems are going to play out. And really, you know, we did a lot of talking around this, but really, when it comes down to it, the only thing that changes from one problem to another is where you put the ones, which is based on, you know, your compact form or possibly on a truth table or something else. But you fill in the ones, you cover your ones with big rectangles, and then you write the expressions corresponding to those rectangles. So just for completeness, let's use a K-map to write a minimized product of sums for the same expression. And so for a product of sums, you want to fill in the zeros and the don't cares. So that's a 0, 0, 0, 6 is a 0, and then these are don't cares. And then you try to cover your zeros with few large rectangles. And so what's a possible covering for the zeros on here?
The rightmost 2, and then you can pair up the 2 next to them.
So we can cover these 2 with a 2 by 1, and then we could pick up these 2, but always try to make the biggest rectangles possible. So let's wrap these and make this a 2 by 2. Alright, so what's this expression here? A is a 0. B changes, so it doesn't matter. C is a 1. And D is a 0. For a product of sums, we want to write a max term. And remember, with max terms, it's the ones that get bars on top. So this would be A or C bar or D. And then this 2 by 2, it looks like A is a 0 here and a 1 here, so A doesn't matter. B is a 0 in both rows, so B has to be 0. C could be a 0 or a 1, D has to be a 1. And so this would be B or D bar. And then our final expression, f of A, B, C, D, would be equal to the product of those two sum terms. And this should be exactly the same equation as this. They should have exactly the same truth values. They should be equivalent to each other. And if you start to multiply these out a little, I mean, I can see that, I'm going to have a C bar ANDed with D bar. That's going to be this term. I'm going to have a B ANDed with a D. That'll be this term. But it looks like I've got some extra terms in here. But I don't know. I shouldn't play without a safety net, but let's take a minute and do some Boolean algebra. I haven't tried this. But let's see if we can turn this into this. So you can FOIL, right? So multiply A by B, A by D bar, C bar B, C bar D bar, and then D, B, and then D, D bar. So we're fine with the C bar, D bar. That's going to be one of our terms here. We're fine with the BD. That's going to be this term here. D ANDed with D bar is equal to what? Say again? Yeah, 0. Right? Because D and not D can never both be true. So this will just be 0, so we're going to OR with a 0, which doesn't have any effect. So what we're left with is AB or AD bar or BC bar. And somehow this ends up being equivalent to this. And I will not take time right now to do that. But if you want a fun exercise, see if you can work this algebraically and get it into this form to show that it's equivalent. And probably you're going to have to add some other terms to it and then combine some things. But you should be able to get there. I might do that offline and show you next time. Alright, but anyway, that's how K-maps work, right? And product of sums just cover the zeros and write max terms for each block. Well, write sum terms for each block. Sum of products cover the ones and write product terms for each block. And dashes cover them if they get you a better cover. Ignore them otherwise. So we looked at some examples of strange coverings last week. In particular, the case where everything was a 1, or the case where everything was a 0. Let me show you your worst possible K-map. Right? So the only way to cover this is a bunch of 1 by 1 rectangles. And remember, a 1 by 1 rectangle is just going to be a min term with 4 things being ANDed together. And so you don't really get any benefit from doing a K-map. So these checkerboard patterns don't work well with simplification through K-maps. But it turns out when you have a checkerboard, you're probably looking at something related to an exclusive OR. So if we just go with 2 variables and think about A XOR B, remember an XOR is just like an OR, except if both inputs are 1, the output goes back to 0. So if we did a little 2 by 2 K-map, this is a 0, this is a 0, this is a 1, this is a 1, there's your checkerboard. So if I tried to write this as a sum of products, I would cover these with 1 by 1 rectangles, and I would say, this is A bar B, this is A B bar, and we OR those together. Well, that's a sum of product representation for an exclusive OR. It says A should be 0 and B should be 1, or A should be 1 and B should be 0. So if you get a checkerboard, or if part of your K-map has a checkerboard pattern to it, think about XORs. And chances are, your sum of products or your product of sums will end up having lots of big terms in them, but there may be a way to do an exclusive OR. And if we go to 3 variables, so if we do A XOR B, it looks like that. If we take that and we XOR it with C, that's the XOR of these 2 columns. And so this is 0, 1, 1, 0, 1, 0, 0, 1. And if we do a 3 variable K-map, this will be 0, 1, 1, 0, 1, 0, 0, 1. There's your checkerboard. So again, a sum of products would be 4 terms ANDed together. Each of those terms would be 3 variables. A bar, B bar, C, A bar, B, C bar, and so on. Right? It's a really expensive circuit to build, but it's also just A, B XORed, and then take that and XOR it with C. And we're going to see this in our next lab. We'll go over that lab on Wednesday. But that's going to involve building something that'll do addition. And XORs are most popular when we're doing addition of binary numbers. That's where they pop up the most. All right. Other questions on the homework, K-maps, things like that? Let me show you one more trick on K-maps. Suppose I had ones. If I have a pair of ones here, I know I can wrap a 2 by 1 rectangle and cover both of those in a single rectangle. I can actually, if I have all 4 corners, I can wrap in both directions and cover these with a single 2 by 2 rectangle. And if this was A, B, C, D, this broken up rectangle would look like A could be a 0 or a 1, doesn't matter. B has to be a 0, so it's B bar. C can be a 0 or a 1, so it doesn't matter. D has to be a 0, so that's B bar, D bar. So you can wrap corners like that. And this I'll take a break after this. This wrapping business is not actually as mysterious as it might seem. So here's your K-map. Suppose I drew another copy of this K-map right here. And suppose I've got my truth table where these two terms are ones. Well, if these two terms are ones, right, these two terms are ones, it's really clear now that I've got a 1x2 rectangle right here. Well, this rectangle is the rectangle that I get if I simply take one rectangle and wrap it from here to here. And if I have ones on the bottom, and I replicate this K-map down here, so I've got ones there, and then I make one more replication of it over here, and I put my ones in here. Well, now it's really easy to see, hey, I've got a 2x2 rectangle right here. Well, what points are that rectangle covering? The points where I'm covering the point 1, 0, 1, 0. That's this corner right here. This corner right here is 1, 0, 0, 0. Well, that's this one right here. This lower left corner is 0, 0, 1, 0. That's this corner up here. And this lower right corner, 0, 0, 0, 0. That's this corner up here. So by allowing these coverings to wrap, all we're doing is saying, hey, you know, I wrote down CD and I came up with this arrangement, but if I had written DC, right, these ones would have gotten moved in over here, and I'd see that these two ones were adjacent to each other. And so the wrapping is just another form of saying, you know, we want to look at our original truth table and all possible arrangements of the input variables to try to find things that are adjacent to each other in terms of differing by only one input variable. And the other way to see it is just imagine that you had a whole bunch of these K-maps sitting next to each other and you're trying to cover the ones like that. If that's helpful, cool. If not, don't worry about it. It's another way to maybe see why this wrapping business makes sense. But it's one of those things that even if it doesn't quite make sense, you can still use it and still get good coverings. All right, let's do a 5-minute break. We'll come back and we will talk about different types of gates and logic operations, and we'll start moving towards programmable logic. And then Wednesday we'll start talking about adders. So let's come back in about 5 minutes, and we'll jump back into more stuff. So I'll see you at 9:09. All right, see you in a few. on what?
Basil.
Oh.
I watered it today. So see
Okay.
if that
Find
helps.
it with dirt from out here.
No, I used the dirt it came with.
Okay. Should be good.
A little bit of dirt from out there. Mixed with it.
Yeah, I mean, some of this looks like it's trying. I don't know. I would not give up on it.
Okay.
I don't think mine had more sun than that. I don't know. These windows might block like critical UV.
Although the ones in the kitchen are doing well,
That's true.
but they are a cactus that are working, so it's different.
Well, yeah. All right. So any questions about any of that? All right. Well, let's talk about nans and nors. We haven't talked about those much. So let's think about Boolean functions with two input variables. And so here's a, b. And we know what the OR of these looks like. It's a 1 when either of the inputs is a 1. In other words, when a is a 1 or b is a 1. And so that's just an OR. And it looks like this in a logic diagram. So if we complement this, we get what's called a NOR. And a NOR is written like an OR but with a little bubble on the end. And it's just take the complement of the OR value. So this is a 1, 0, 0, 0. That's a NOR operation. And a dual to that comes from the AND. So if we do an AND, which looks like this, that's a 1 if A is 1 and B is 1, so it's got a 1 in that last row only. And if we complement that, we get what's called a NAND. The logic symbol is an AND with a bubble on the output. And we get the values by just complementing the values for an AND. So this is a 1 everywhere except when both inputs are 0. And these are interesting functions. And we don't necessarily design a lot with them when we're doing engineering 250. But they are extremely useful functions because of De Morgan's theorem. So who remembers De Morgan's theorem? So it's almost that adding is the same as it's almost that ANDing is the same as ORing, but you have to do this funny thing with the complements. So if we want to take A or B and change it to an AND, well, the complement of A or B is the AND of the complements. And the complement of A and B is the OR of the complements. So it lets us move between ANDs and ORs by changing what we complement. And that's the first thing that's interesting, is we can go between an AND and an OR if we can do negations or complements in some way. But the other thing, and let's just put a NOR truth table. So that's a NOR gate. So it's the opposite of an OR. And let me just look at the values where B is equal to 0. So just looking at these two rows of my truth table, which are the rows where B is equal to 0, can you see an easy way to describe what the NOR of A and B are? So just looking at this truth table, just these two rows, ignore these other rows. Are these output values related to something simpler than a NOR? It's just not, well, B is a 0, so B naught is a 1, and this is not always a 1, but you're on the right track. A naught, exactly, right? This is just equal to the complement of A. If A is a 0, this is a 1. If A is a 1, this is a 0. And that's just what the truth table is doing, right? There's no sort of divine reason for that. But if I just look at the rows where B is a 0, the NOR is the opposite of the A input. And so I have this cool little fact, A NORed with 0 is always equal to not A. Which means if I have a 2-input NOR gate, and I feed A into one side and I connect the other side to ground, it acts like an inverter. So you can build an inverter out of a NOR gate. And how do you do that? Simply connect one of your inputs to ground. The same thing happens with NANDs. And in this case, I'm going to look where B is equal to 1. And if B is equal to 1, the NAND is equal to, again, the opposite of A. So A NANDed with B is the same as A bar. Which means A ANDed with 1, negated, is just A bar. So if I happen to have a NAND gate sitting in my parts box, I can take one input, tie it to a logic 1 by running it through a resistor to 5 volts. I can take my input, the output will be the complement of A. So you can invert with NANDs and NORs. Well, if I have a NAND gate and I run that through an inverter, I've got an AND. Right? The output of the NAND is the inverse of A and B. This will be the inverse of the inverse. So this will be A, B bar. This will be A, B double bar, which is just A, B. And I can make this inverter using a NAND gate. So if I really wanted to do an AND operation, I could get there by taking AB, running it through a NAND, connecting B to logic 1. Sorry. Take AB, get AB bar, and then take this, run it through a NAND gate, take the other input, run it through a logic 1. This is AB. And if I have AB and I run it through a NOR gate, and then I run that through a NOR gate with one input connected to ground, that gives me an OR gate. So what does this mean? This means if I have a NAND, I can get a NOT. I can use that to get an AND. And can I get an OR from an AND? Right? I can get a NOR from an AND. All I have to do is take my inputs, negate them, AND them together. That'll give me a NOR. And if I run my NOR through another inverter, I'll get an OR. So if I have a NAND gate, I can get AND, OR, NAND, NOR, and NOT. And if I have a NOR gate, I can get an inverter. I can complement my NOR to get an OR. If I know how to do an OR, I can also do a NAND. And I can run the NAND through a NOT and I can get an AND. And so the nomenclature here is a NOR gate is universal. We can use a NOR gate to build any other logic gate that we want. And the NAND gate is also universal. And since we know we can take any truth table and write it as a sum of products, to do a sum of products, what do you need? You need to do ANDs, ORs, and NOTs. Well, if you have NOR gates, you can do ANDs, ORs, and NOTs. If you have NAND gates, you can do ANDs, ORs, and NOTs. So theoretically, we could build a circuit to implement any truth table using just NOR gates. Or using just NAND gates. And it's cumbersome. It's not an entirely fun thing to do. But you can do it. And you've got a homework question in your next homework set that involves doing just that. And it's not just an academic exercise. So in the early 60s, when President Kennedy announced to the world that we were going to go to the moon, of all things, and send somebody there and bring them back safely, and then said, okay, go do it. Pretty early on, people realized we really wanted computers on board the ships that were going to be involved in this. Primarily the orbiter that was going to go around the moon and land and so on and so forth. Computer control was pretty essential, right? Computers weren't really a thing in the 60s. They were these big, room-size behemoths made by companies like IBM, and trying to launch something from the Earth and reach escape velocity to get away from the pull of gravity, right? You're looking at grams, right? An extra gram costs you, X thousands of dollars in fuel and so on and so forth. So how do you put a computer on board this system that's supposed to, leave Earth's gravity and go into orbit around the moon? And so people came up with a radical suggestion that they were going to use these newfangled things called integrated circuits. And, ICs were developed in the late 50s. Before that, things were made out of, transistors and then relays and vacuum tubes originally. And you couldn't just walk into the STEM building and open up your parts box and pull out some chips, right? Chips weren't commercially available. So the government had to contract somebody to build these integrated circuits that would be used for the guidance computers. And designing a chip from scratch is phenomenally expensive, and especially, in the early 60s, it was very experimental. And you could expect that, a good portion of the chips that you would make would not work. They would just have, defects in them and such. And so this was a huge undertaking. And Lincoln Labs, a research wing of MIT, was commissioned to come up with, the integrated circuits that would be used in this computer. And so here's a schematic of one part of the guidance computer, and you can find these online. And the really cool thing about this is the whole thing is made out of NOR gates, right? Everything in here is a NOR gate. And why did they do that? Because why build 2 or 3 or 4 different kinds of chips if you can get away with just building one? So they developed a way to create these integrated circuits that performed a single operation, which was NOR. And then they used this universality of the NOR gate to implement other kinds of gates. For example, here you've got a plain old NOR gate, but here you've got one input going into a NOR gate. Well, that's doing an inverse, right? Because the other thing I didn't show in the truth table, if you NOR something with itself, you can get simpler logic. So this was an actual real world application where this universality of NORs was used to design the entire computer using just this one type of gate. And it takes more gates this way, but it takes fewer types of gates, and the trade-off was apparently worth it to have a more complex circuit but not have to develop ands and ors and knots and just use this one type of NOR gate. You also see a lot of these situations where you have pairs of gates with the output of one feeding the input of another, and the output of that other feeding the input of the first one. This is something we're going to start talking about probably Wednesday, definitely by Monday. This is called a flip-flop, and it's a way that you create a 1-bit memory using these gates. And this is the way that fast memory, cache memory, for example, is created today. And this is how we're going to do the second half of this course, which will be looking at what we call state machines. So circuits that have memory, circuits that remember what has happened in the past and are affected in what they do now based on what happened previously. And the key to making state machines is going to be having some way to store 1 bit of information. That's what these pairs of cross-coupled NOR gates do. And we'll see how to create these flip-flops with NOR gates or with NAND gates, and we'll study how they work. We'll see how to analyze them, and then we'll build up more sophisticated types of memories using these cross-coupled components. So this is something we still use today, and it's another possibility when you have these inverting logic gates, NAND gates or NOR gates. And you can use NANDs just as easily as NORs. So that's another preview of coming attractions. But for now, the punchline is you can build any circuit you want with just NOR gates or with just NAND gates. So there's some homework questions on that. All right, so we're moving into more complex types of gates and logic functions. We've got, and nor, not, XOR, XNOR. These are basic logic operations. But there's more complex types of things we might want to do to turn inputs into outputs. And so the next one I want to talk about are called multiplexers. And they're usually just called muxes. And you can find all of this in the book. It should be in chapter 3 of the textbook. But here's a simple version of a multiplexer. So we have two inputs, I0 and I1. And we have another input called select. And then we have some output. Alright, so this is a 2 input, 1 output multiplexer, sometimes just called a 2-to-1. And let me show you the truth table, but then let me tell you what this actually does. So it's got 3 inputs. And here's what the output looks like. All right. Nothing too startling here, right? We could write a sum of products for this. We could say output is, select bar I1 bar I0, or select bar I1 I0, or select I1 I0 bar, or select I1 I0. Nothing too exciting there, but a different way to look at this is as follows. If select is equal to 0, the output is exactly the same as input 0. If select is equal to 1, the output is exactly the same as input 1. Does everybody see that? The output either matches input 1 in these cases, 0, 0, 1, 1, or the output matches input 0, 0, 1, 0, 1. And the choice of which of those is going to happen is exactly determined by this select input. So if select is 0, it's as if this input is connected to your output. And if select is 1, it's as if this input is connected to your output. So this is sometimes thought of as like a steering circuit. It's a way to choose one of 2 inputs to send to the output of this block. And the select line is the thing that makes that choice. Should we send this input to the output, or should we send that input to the output? And a lot of what goes on inside a computer, inside the CPU of a computer, is a bunch of steering of signals. Where we might have 2 things coming in here and we want to send one of them to some output piece of a circuit. And I'll give you a kind of simplified example. Suppose you're building a computer and you want to add some things together. And maybe you want to, let's just increment something. So suppose we want to do something like, x plus 1. Or maybe we want to do something like y plus 1. So we could use a 2-to-1 selector or multiplexer. We could put x in here, y in here. We could take the output and feed that into an adder. And the other end of the adder could be a 1. And this could be a select. And now by just changing the value of this between 0 and 1, this output will be either x plus 1 or y plus 1. If we select, let's say this is input 0 and this is input 1. If we set select equal to 0, x will go through the output into the adder. We'll add 1, this will be x plus 1. If we set select to 1, then y will come to the output of the multiplexer. We'll go into the adder, so this will be y and 1, and the adder will give us y plus 1. And so if you look inside a typical CPU, you'll find an area called the data path, and the data path is really a whole bunch of multiplexers that are basically taking different things that we might want to operate on and connecting them to the inputs of other things and routing them through or steering them through the circuitry to perform whatever the low-level instructions of our computer are asking it to do. So Engineering 270 will dig into, what goes on inside a CPU and how these low-level operations, what these low-level operations are, and to some degree how they work. And it'll be basically multiplexers driving the whole thing. Alright, so let me show you a different way of representing this truth table. And this is something called a compressed truth table. And it's actually an easier version of this. This is a truth table with 3 inputs, 8 rows, 8 outputs. Doesn't necessarily tell us what's going on. Let me redraw this in a slightly different form. This is the same information as this. It says if select is 0, the output will be equal to whatever the input I0 is. 0, 1, 0, 1. If select is equal to 1, the output will be equal to whatever I1 is. 0, 0, 1, 1. But this is a much simpler truth table, right? It's got 2 rows, it's got 2 columns. This had 8 rows and 4 columns. So this is called a compressed truth table. It's a compressed version of this. And the advantage is it logically tells us how the output is related to the inputs. In particular, if the select input is 0, I1 has no effect on the output. And the output's exactly equal to I0. And so from here, I could actually create this truth table. Right? How would I do it? I'd write all 3 of my inputs and I'd say, hey, if select is 0, I'm going to set my output equal to I0. Okay, my output will be a 0, 1, 0, 1. If select is 1, which is these 4 rows, my output will be equal to I1, so it should be a 0, 0, and a 1, 1. So you've got the same information in both of these, but this is in some ways more meaningful to us. And it really captures this idea that what the output is doing is just reflecting one of the inputs based on what the select value is. So it's either taking this, sending it to the output, or taking that and sending it to the output. Alright, here's a 4-to-1 multiplexer. It's got 2 select lines, 4 inputs, and 1 output. The truth table for this would be 6 input variables, that's 64 rows, 2 to the 6th, and 1 output. But if I compress this and I give you a truth table that sort of functionally tells me what's going on, here's the compressed version. Right, that's exactly what this circuit does. it sets the output equal to one of the input values. If I set my input to 1, 0, my output will be equal to I2. 1, 0, I2. If I2 is a 0, output will be 0. If I2 is a 1, output will be 1. And with these set to 1, 0, input 0, 1, and 3, no effect. And so we can think of the output as being connected to input 2 if our input is 1, 0 on the select lines. And this is just like a programmable wire. And we can choose, do we connect the output to either I0, I1, I2, or I3? But it's really just logic, right? I could write this as a 6-input truth table. I could do a sum of products. I could come up with an equation for the output in terms of the input. Is this making sense? I'm going to keep going unless there's questions. Alright, so one of the cool things you can do with multiplexers is you can use them to make multiplexers. So this 4-to-1 multiplexer, as I've said, it's got 6 inputs, 64 rows in the truth table, and half of those output bits are going to be 1. So we're going to end up with 32 product terms, and then we're going to need a 32 input OR gate. That's a really, really complex circuit. But let me show you a different way to make a 4-to-1 multiplexer by using a few 2-to-1s. Alright, so here's a 2-to-1, here's a 2-to-1. Here's the select lines. Let me label them inside. Here's the select lines. So I'm going to do I0, I1. I'm going to put I2 in here, and I'm going to put I3 in here. And I'm going to take these two outputs, I'm going to put those into a third 2-to-1. And here's our output. And I always have to think about what order to put these bits in. So I'm going to take bit S0 and feed that into this muxer select and this muxer select. And that's going to choose either I0 to come out here and I2 to come out here, or I1 to come out here and I3 to come out here. And then we're going to take one of those two bits that came out from here and select one of them for the final output. And this will do the same thing as this. And you can work through it with some examples, but for example, if S1, S0 equals 1, 1, well, since S0 is a 1, I3 will come out here, and I1 will come out here, and then since S1 is a 1, I3 will get selected to the output. And so S1, S0 is 1, 1, your output will be I3. Well, that's what we want our 4-to-1 to do. If S1, S0 is 1, 0, well, since S0 is a 0, this muxer will send I0 to the output. This muxer will send I2 to the output. And then since S1 is a 1, this muxer will take this bottom input I2 and send I2 out. Well, if S1, S0 is 1, 0, we want our output to be I2. And so if you have 3 2-to-1 muxers, you can make a 4-to-1. And a 2-to-1 mux is a very simple circuit. Right? It's 4 outputs that are 1, and this compresses really nicely in a K-map. And guess what? If you have a pair of 4-to-1s, well, if you have 5 4-to-1s, you can make a 16-to-1. And so one of the things you do with multiplexers is you use them to make bigger multiplexers. And you can buy a 74-154 chip. It's a 16-to-1 multiplexer. 16 inputs, and it sends one of them to the output. I don't think that's a 154, but there's a chip for it. Alright, so multiplexers are useful for steering, but they have another interesting use. So we can use multiplexers to generate general logic. So let's make a 4-to-1. And our truth table again looks like this. So our output will be either I0, I1, I2, or I3. Alright, so there's our multiplexer. And suppose you want to create some kind of logic function. Let's say we wanted to make an exclusive OR. So we want to build a circuit where we take two inputs and the output is the exclusive OR of those inputs. So suppose I want my outputs to look like this. Well, it's really easy to do with a 4-to-1 multiplexer. All I have to do is take input 0, connect it to ground. Inputs 1 and 2 get connected to 5 volts. Input 3 gets connected to 0. This is an exclusive OR gate. And all I need is a 4-to-1 multiplexer. I connect these two to ground. I connect these two to 5 volts. And this acts like an XOR. Why? Because if my inputs are 0, 0, it'll take this input line, which is at 0 volts, and send that to the output. My output will be 0. If my inputs are 0, 1, it will take whatever's coming in on this line I1, which is 5 volts, logic 1, send that to the output. My output will be logic 1. Let's say I wanted to make a NAND gate. So a NAND gate, I want my output to look like this. Well, how do I do that? Just take a 4-to-1 multiplexer, tie that first input to 5 volts, tie the other inputs to 0 volts, ground. Bingo, it's a NAND gate. Maybe I want an OR gate. So an OR gate, I want my outputs to look like this. Take my same 4-to-1 multiplexer, connect this first input to ground, connect these three inputs to 5 volts. Bingo, it's an OR gate. So this is almost like, a universal gate. And to change it from one thing to another, all I have to do is connect these inputs to whatever values I want. There's some homework questions that play with this too. So if you find yourself on a desert island with a protoboard and a whole box of 4-to-1 multiplexers but no other logic gates, you're okay, right? If you need an AND gate, just take this 4-to-1, connect these inputs to 0, this to 1. It looks just like an AND gate. There's your two inputs, there's your output. And the output will be 1 exactly if the two inputs are 1. So this is the other thing we do with multiplexers. So multiplexers are good for steering signals around circuitry, like inside a CPU. They're good for building bigger multiplexers. And they're also good for doing general logic. If you have some truth table you want to implement, you can do it with a multiplexer. If you had a 16:1 multiplexer, you could implement any logic function of 4 inputs by just hardwiring the 16 input lines over here to the 16 values you want your truth table to produce. Take your input variables, feed those to the select lines, and it will choose one of these 16 values to send to the output. Alright, the flip side of a multiplexer is a demultiplexer. And so a demultiplexer looks like this. Well, let's just do a 2-input one. So with a demultiplexer, this is like a 1 to 2. We have a single input, we have 2 outputs, and we have a select line. And the way it looks is as follows. I'll show you the compressed truth table. So if the select line is 0, output 0 matches the input. If the select line is 1, output 1 matches the input. And what should the unselected output be? Well, I'm just going to do it as zeros, but it could be ones, could be something else. But here's a possible table for a 1 to 2 demultiplexer. And the sense here is we can control whether the input line is connected to this output or that output. So this is the other side of kind of a steering circuit. We can take this input and say, hey, I want to send it to output 0 by putting a 0 in here. Or we can take this input and say, hey, I want to send it to output 1 by putting a 1 in this select line. And now this input goes down here. And output 1 matches the input. And so with a multiplexer, we can choose an input source to feed into some circuit. With a demultiplexer, we could have we could take the output of some circuit and send it to a number of different possible locations. We could say, let's send this into a memory unit, let's send it into a network adapter, let's send it into somewhere else. And demultiplexers can get big. So here's a 1 to 4. And our outputs are sometimes called Y, so Y0, Y1, Y2, Y3, and a pair of select lines. And we can choose whether the input should get routed to here, 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 or here. Alright, so where does this leave us? Alright, so Wednesday I want to take a little bit slower, deeper look at these demultiplexers and see how they go along with multiplexers and how we can do some things like send information over a single line, send multiple bits of information over a single line. And then I want to look at the data sheets for a few of these and just kind of see how those data sheets look, see the compressed truth tables, the wiring, and so on and so forth. And then I want to talk about something totally different, which is called programmable logic. And programmable logic is a way to do this sort of systematic circuit design that we've been doing. How to take advantage of this with a particular type of hardware device called a programmable logic array or a PAL or a PROM. So we'll talk about that, and then I want to move on and talk about doing addition, and this will take us into Lab 4. So we'll go over Lab 4 on Wednesday, talking about adders and half adders and full adders and so on. And then if we finish that, we will start moving into the next part of the course, which is looking at circuits that change over time, moving into what are called sequential circuits and eventually state machines. And that will basically take us into where we'll be for Engineering 270, which if you're taking it in summer will be the next thing after this course. All right, so office hours tomorrow morning, 7:30 to 9. If you've got questions, come by then. Otherwise, I will see you in class on Wednesday. All right, thanks.